We're looking at question number 8, and this question is about energy transfers. It says, figure 11 shows a toy car in different positions on a racing track. So you've been given different locations, A, B, C, and D. So before I look at the question, let's quickly assess the situation. What type of energy will be involved at location A, B, C, and D? So at location A, if I assume that there is no loss of energy taking place, then I can say here it will have GPE. As it starts moving down, the GPE will decrease, and at this location, the car will now have GPE plus KE. At location B, there will be no GPE, provided that location B is on the ground. So I can say here it will only have KE. Location C is above ground. So again, at location C, the car will now have KE plus GPE. And then when the car rolls down and gets to location D, it will now have KE. I'm going to use numbers for these locations. So 1, 2, 3, 4, and 5. So if I assume that there is no loss of energy taking place, then the energy at location 1 will be equal to energy at location 2, and this will be equal to location 3, 4, and 5. But if I do consider losses, for example, due to friction, some energy will go into the surroundings. In that case, 1 will now become bigger than 2, 2 will become bigger than 3, 3 will be greater than 4, and 4 will be greater than 5. The question says the toy car and racing track can be modeled as a closed system. So a closed system is one where no energy can enter into it from the surroundings and no energy can go into the surroundings. It says, why can the toy car and racing track be considered a closed system? Let's quickly have a look at the given options. The first option here says the racing track and the car both have gravitational potential energy. This statement is true, but we can't say that because of this, it will be considered as a closed system. Option 2 says the racing track and the car are always in contact with each other. Again, this statement is true, but this is not the reason for the system to be classed as a closed system. It says the total energy of the racing track and the car is constant. So in this case, no energy is entering into the track or the car from outside, and no energy is going outside from the car or the track. So the answer is this. The next part says the car is released from rest at position A. From rest means it does not have any KE at location A and accelerates due to gravity down track to position B. They've given us the mass. They've given us the vertical height between position A and position B. This is 90 centimeters. This is the value of H. Now you need to remind yourself you can't use H in centimeters. So you'll have to perform a conversion here. So you'll do 90 divided by 100. And this gives you 0.90 meters. They've given us the gravitational field strength. In other words, this is the value of gravity, which is G. It says calculate the maximum possible speed of the car when it reaches position B. Maximum possible speed. This will be no loss of energy has taken place. So if I go back, location A is here, location B is here, and we already worked out at location 1 you will have GPE, and they've confirmed that at location A it is released from rest. At location B it will have KE. So simply I have to do GPE equals KE. GPE is equal to KE, and I'll replace GPE and KE with their formulas. GPE is M times G times H, whereas KE is half times M times V squared. Now, if you look at these two sides, all variables are being multiplied. So what we can do in this case is we can say that this M and this M will cancel out each other. Now I can replace them with the values. I've been given the value of G as 9.8. Been given the value of H as 0.90 equals, I do not know the value of B, so I'll leave it as B squared. If you multiply the numbers on the left side, you will end up with a value of 8.82, and on the right side it will become v squared over 2. Put 1 in the denominator. When you cross multiply, you will end up with 17.64 equals v squared. To get rid of this square, you'll have to take square root on both sides, and that will leave you with an answer 4.2 meters per second. The last part of this question says figure 11 is repeated below. It says at position C, the car's gravitational potential energy is 0.20 joules greater than at position B. So this statement is important here. This statement means that when the car travels from B to location C, the change in GPE is 0.20 joules. The question says how much KE does the car need at position B to complete the loop of the track? Give a reason for your answer. So we've been given 3 options and we have to choose one of them, and then we also have to provide a reason for the selected choice. Option 1 says less than 0.20 joules. If we say that the energy at location B is less than 0.20 joules, then the car will never get to location C. So 1 is not correct. Second option says exactly 0.20 joules. Now, if the car has exactly 0.20 joules of KE at location B, the car will get to location C, but it will not have any KE at location C. So it will not carry on traveling. It will just simply fall off. Then the next option says more than 0.20 joules. This option makes more sense. Why? Because if it has more than 0.20 joules, then out of that energy, 0.20 joules will get converted into GPE here. And the remaining energy will remain as KE. So the car will carry on moving and will complete the loop. So the answer is this. We do need to give a reason for our choice. We will say here at location C, car must have GPE plus KE.